Hello, everyone. Super excited to be here learning about Stylus. It's incredible. I always thought that there would be new virtual machines, better ones to build applications. And so, yeah, so I was thinking about what we do in Fairgate, how does it apply to Stylus, how can we use Stylus, why we need Stylus, and I'm going to tell you what are we doing currently in Fairgate, and why there is a very good match with the Stylus. So first of all, uh, why breaching requires computation? Because you need at least to be able to verify the consensus of another chain, or in the case of an optimistic rollup or optimistic breach, you need to be able to dispute and verify at least one small step of the computation. So there are a lot of techniques to compute in a blockchain, and some of these apply to Bitcoin, some do not. But we are interested in this new paradigm that is called disputable computation, also known as optimistic computation, because it's very cheap when there is no dispute. Like if there is no dispute, it's just posting something on chain, as Arbitrum does with the state updates that it posts. And then only if there is a dispute, we have a lot of work to do. But if not, then it's very cheap. So there are precursors of this technique in Ethereum. The first project that started doing this was TrueBit. Then optimistic rollups as Arbitrum came and make fully use of this technique. And there was no way we could do this in Bitcoin, right? And up until 2023, where Roman Linus created a method to do optimistic computation, disputable computation on Bitcoin. So, you know, computing on Arbitrum is very cheap, and with Stylus it's cheaper. And computing on Bitcoin, it's impractical and expensive, but it's not impossible. Since we have BitBM, it's not impossible. So we can build optimistic breaches from Bitcoin to any other chain. But something very bad happened in 2010. Satoshi, someone reported a bug in one of the Bitcoin opcodes. There was a right shift. And so Satoshi disabled a lot of opcodes, just a measure of war, you know, to try to first take a look and see if there was any problem. And then he disappeared, right? Two weeks later, we know that the CIA met with Gavin Andreessen, and Satoshi preferred to disappear. So he left us with this horrible thing that now we cannot compute any of these opcodes. So he disabled a lot of very important arithmetic opcodes, right? And what is left in Bitcoin is, if I want to do a multiplication, something as simple that you would do with in Stylus with just one instruction, you would need 3,575 Bitcoin opcodes to do just a 32-bit multiplication. This is the problem, and this is the whole script, right? You cannot see it, but if you in my screen, you can see every single instruction is there. There's a lot of op drops at the end, and this is terrible, right? But we can fix this. So what is left in Bitcoin is kind of two universes. What is called small script, what is called big script. These two words are not connected, just by a few instructions that are worthless, and so it's a real pain. But we have this new technique that we have mastered that is called BitBM, and it works pretty similar to what you do in Arbitrum to do these state updates. So what's this? The precursors, as I mentioned, of this fraud-proof paradigm are the Blockstream sidechain paper of 2014, where Blockstream introduced a new opcode, reorg verify, to be able to prove that certain chain was not the honest chain. Then TrueBit, optimistic rollups such as Arbitrum, and then some new techniques in Bitcoin that are Lamport signature verification. So instead of Schnorr on ACDC or ACDCA, somebody find a way to implement Lamport signatures on Bitcoin, and that allows you to put state on Bitcoin and have immutability of state during several transactions. So that's great. So this new paradigm to verify computation on Bitcoin has currently 4 flavors. The BitBM2, which is a single ROM protocol, the BitBM3S, which uses completely different technique. It's called garbled circuits. It's a cryptographic technique. And we are developing two of these verification technologies. One is the BitBMX CPU, which is a RISC-V CPU that you can dispute on Bitcoin. So we use Rust and the same tools that you would use to write contracts with Stylus, you will use them to write contracts on Bitcoin, okay? Because there you have a very low-level machine, and then you can write your contracts in any language, C++ or these other languages. And the next thing we are working on is also using garbled circuits. But since we have very little time, I'm not going to go deep on this. So what's the idea of verifying a computation of a CPU on Bitcoin or on Ethereum? Basically, you break your function, the computation, into a lot of smaller functions, which represent smaller parts of the computation. In our case, we use very, very small f's, right? Each of these functions is just one RISC-V opcode. It could be a WASM opcode, but we choose RISC-V opcode. It's similar choice. And then if you apply all the functions, you get to the final result. So basically, you have a chain of functions that you can run locally, and you execute all these RISC-V instructions. And what happens in the chain is like there is a Bitcoin transaction that posts only the latest state. This set 1 and 2 are the mid state, right, of the computation. Only the latest state is posted, and then there is a binary search, a bisection search. We in practice do NR search to make it faster, and so you can ask the other party to post a mid state, and then you do recursively until you get to a point where you find this single instruction that misbehaves, like it's a failure, and then you can go and challenge that single instruction. Okay, very similar again to what Arbitrum does when it has to exit and post the state on Ethereum. Okay, so this is how it works. In a binary tree, you get a malfunction, then you can challenge that. So the RISC-V CPU is it's an open source, license-free, very well supported CPU. Such as it's very similar to WASM, so it has standard architecture, RISC architecture, very simple to implement on Bitcoin. We had to implement every single of these opcodes on Bitcoin to be able to challenge each of these opcodes. And our next technique is even more off-chain. So it really puts very, very low amount of computation and data on-chain. Is using a cryptographic technique. It's called garbled circuits, which is a kind of multi-party computation thing, where you basically code all your predicate, everything you want to verify, if it's a snark or if it's a peg out or a withdrawal from a second layer or whatever, you put this on a single circuit, right? And then basically you use something called this conditional disclose of secret, where only if the input satisfies the circuit, you get one specific hash, one specific result that allows you to either penalize the other party because he's misbehaving or allow the other party to continue. So basically on chain, what you have is a single hash time lock. Very, very simple construction. So this is how it looks in terms of cost when you want to verify this on Bitcoin. If I had to verify the whole withdrawal of a breach on Bitcoin, it would be like 800 gigabytes of Bitcoin script. If I just want to verify snark, it's still 8 gigabytes of Bitcoin script, so it doesn't even fit into 1,000 blocks. BitBM2 basically is one way of cutting this snark verification into functions, F. It uses very big functions, like each one of these functions takes a full Bitcoin block of computation. It's not what we do because it's very, very expensive. A challenge can cost you 100 grand, okay? So imagine you don't get decentralization. If you use this for some sort of exit from a second layer, then only very few participants will be able to challenge, right? Because it's very high cost. Our CPU has a very low cost. It takes only 400 kilobytes on this. This is about $400 to dispute. And using garbled circuits, we could put it down to 4 kilobytes. Okay, what are the limitations? This is part of the BitBM limitations. There is a new kind of security condition or security assumption, which is called the 1 of n honesty. It's not like fully permissionless because there is a committee but it's enough that one of these participants of the committee is honest, which is much, much better than the traditional federation approach, okay? So you get very, very decentralized bridge. And you can even have covenants. We've made it possible to have covenants on Bitcoin under this trust substantial. So you can pay anyone, you can create Bitcoin DAOs, and it's very capital efficient. So what's the benefit of this one of an security assumption is like you don't get, in a classical federated model, you cannot let anyone come in or be permissionless because they can come, they can cyber attack the protocol and get control of the funds and take the funds, right? So this does not work to be in a permissionless protocol. But we have these two extremes. This is a federation model, T of N. This is the Arbitrum model, like one of infinite, like anyone could challenge. If it just posts the security bond, it's enough. It could be high, it could be low, but it's enough, anyone can challenge. Well, there is something in the middle, which is basically, if it works, let's see. Okay, it's the BitBM style where it's kind of in the middle. You have a committee, but just you need one. So you can make these committees very large if you want. So the good thing about this is like if you are a honest party and you are participating in one of these committees, the committee size can grow. You don't care. You don't care if anyone comes and registers and stakes because basically you always get to be there and protect the bridge. So what's happening in this year regarding BitBM? Well, there's some colors missing here, but there are many, many Bitcoin sidechains that are opting to launch on this technology. Some very well-known names are integrating with Bitcoin, with BitBM. For instance, Cardano, we built a bridge for Cardano to have Bitcoins directly and in a decentralized manner move to Cardano, Alpen, building on both, Citria, Roosstock, obviously, and many more, Fiamma, Gold Network. So this is the technology that is enabling new bridges, new type of bridges, more decentralized bridges. And so we build this platform as an open source project, collaborative project. Basically it integrates several verification technologies. So we are not stuck with our BitBMX CPU. You can use new verification technologies based on the Gebhardt secret, but it gives you all the components. First of all, who is pushing for this technology right now? There are 3 companies that are kind of putting some resources to make this open source and everything. Is Fairgate, Roosstock Labs, and Input Output. And we basically are focused on these 3 projects: the CPU for verification, the whole platform, so you can build your own bridge very easily, or it cannot be only a bridge. It could be anything you want to build on Bitcoin based on having kind of a DAO, Bitcoin DAO, or something like that, a multi-party protocol, and the garbage sequencing. This is how it looks, the code base. Like you have several modules that abstract you from doing, like the protocol beadle lets you just describe your protocol and it gives you all the it makes the fraud proof for you, so you don't have to care. The transaction monitor obviously makes sure that you react when there is a dispute on Bitcoin. The coordinator does the fee bumping for you. So you get all the pieces for free. And let's see. Okay, so and then we publish this year like a lot more papers, 1, 2, 3, 4, 5, 6, 7, and 4 more papers. So it's like 10 papers of expanding this technology with many features. I'm going to focus on a couple because they are very related to our idea of bridging with Arbitrum. The first one is Flex. So we managed to find a way so that the security bonds that you need to dispute are on demand. So you don't need to put the security bonds for the whole lifetime of the project, like lifetime of the breach. So only when there is a dispute, you go and put your security bond. So you increase the capital efficiency. You reduce, the problem of the opportunity cost of the blocked security deposits, and gives you a lot more possibilities. Also, we implemented covenants under the same paradigm where you can use this to pay to third parties. And we implemented something very similar to Arbitrum Bold for Bitcoin. So we had to solve the same problem of Arbitrum Bold. Arbitrum Bold is a technology that is used to dispute with state commitments from Arbitrum. So we had to implement the same thing on Bitcoin. And so this battle protocol allows you to have a, so Yeah. So most of the protocols first that use BitBM allow only to have about 20 watchtowers, which is very limited. We made a possibility to have up to 1,000 watchtowers with constant security bonds. Okay, so how does it work? Okay, so first, what is the problem of having 1,000 watchtowers or 1,000 operators? You can be cyber attack, right? And you can have to be able to dispute all of them at the same time. It's the same that happened with the Arbitrum Vault, right? So if you are an operator, then maybe all the watchtowers are disputing you at the same time. You don't have enough security funds to, to fight against everyone. Or it can be the opposite. Like there is one watchtower, there are 1,000 operators all posting state commitments, and you cannot basically fight against all of them at the same time. So this is a big problem. It's an even much bigger problem than the verifier's dilemma, right? Which is also affect this fraud proof system. This is very bad. So we managed to implement this on Bitcoin. It solved the disputing logarithm of the number of participants, which is quite good. It requires a fixed amount of security deposits with a setup cost that is to the n square, which is not that bad. It's tournament-based, very similar to Arbitrum Vault, very similar to Cartesi Dave. And I would say it's more efficient than Arbitrum Classic or Optimism because this has this tournament structure. And the hard part here, I would not say this is the design of the fraud-proof system, but to implement this on Bitcoin with the enormous restrictions that you have in Bitcoin. So how it looks, the implementation, well, let's say that you have 1,000 operators, each one claiming a different thing, a different state update, and then you have the challengers. So it splits the tournament in 2 tournaments. In the first tournament, all the claimants, all the parties that have a claim of a certain exit or a certain state, they fight against each other until there's only one winner. And after that, all the challengers that they want to dispute, they organize themselves in this tournament structure. And the good thing is that when you win a dispute, you get immediate reimbursement from the other party's security deposit. So now you can start 2 disputes with the same money because you have earned the money immediately. And then you can go for 4 and then 8. So you double the number of disputes at this round, and that allows you to dispute any number of participants with a fixed security deposit. Okay, so it's kind of trying to solve the same problem as Arbitrum Vault and Cartesi Dave, but with the limitations of Bitcoin. So why it's for us, it's very important to have efficiency on the Arbitrum side, on the sidechain side, because I'm not going to go in detail of all these components, but essentially this is what needs to be implemented on the sidechain or in the secondary chain, or I mean the primary chain being Bitcoin. And we need to implement 2 components. One is this will be the bridge contract, which receives the bridging request. And the other is a Bitcoin SPV oracle. Because having an oracle here allows to have very, very, I would say, detailed management of the security bonds, the payout, how we distribute the payouts among the participants. Like if we put all the security bonds on the Bitcoin side, which is possible, then it's very difficult to get the incentives right because you just have to pay to one operator or one watchtower. And then the incentives break. You need to, make them cooperate in a certain way. So all the watchtowers that participated, that try to protect your protocol, must be paid in a certain way. So that's why the Bitcoin SPV oracle is important. And implementing this on Stylus, it's much more efficient. It does a lot of cryptography, like a lot of hashing. And so if you have to implement this on Ethereum, like there was a project implementing this back in the 2016, it was very expensive. No one wanted to update this oracle because it was very expensive. So I think that in a Stylus, it will be very, very cheap. And well, if you want to follow all these developments and all the developments of the Bitcoin Layer 2s, which is kind of a hot year for Bitcoin Layer 2 this year, you can follow us in our newsletter of computing on Bitcoin. And yeah, this is all I have to say about how we think about bridging Bitcoin with Arbitrum. Thank you very much.